Okay, today's video is on Unit 5, Physics Edexcel International A-Level, and this is the paper taken in January 2024. My students have done it as a mock in April, so I'm now releasing these answers. I would recommend, if you're doing it in your own school, that you check with your teacher whether they want you to have a look at these, because the teachers generally use the most up-to-date exams for practice mock exams. So obviously, if you want to get an accurate prediction of the grade you're heading towards, it's better to check with your teacher. Okay, and then come and look at it once you've done it as a practice paper timed. Okay, we're now up to 160 subscribers. I notice this is a service that I started at the beginning of the year in January, and it's taken off quite successfully, and we're reliant on you sharing our videos with your friends so we get more coverage. And please like the video if you find it useful, because that helps us with the YouTube system. And make sure you subscribe, because I'm doing approximately 2 videos a week on average. Okay, so this is the first section, is a multiple choice, and question 1 is about ice melting at 0 degrees. So basically it's about specific latent heat. Which row of the table gives the changes in mean molecular kinetic energy and mean molecular potential energy? Okay, so kinetic energy is proportional to temperature. Well, the temperature is still at 0 degrees because at transitions between states of matter, so it's going from ice to liquid, so solid to liquid, then all of the energy goes into breaking bonds, and breaking bonds is a form of potential energy, and you're increasing the separation of the molecules. So the mean molecular potential energy should increase. So 2 of them have increased, but there should be no change in the temperature. Okay, therefore there is no change in temperature, therefore there should be very little change in the mean molecular energy, and in fact that gives you 2 ticks in line B, so B is the correct answer. Question 2, astronomers can use stellar parallax to determine the distance to stars. Yes, and these are relatively nearby stars. So the parallax method is basically looking at the difference between, so here's a sun, and the Earth is on the 2 sides of the sun, and you'll say you're looking at stars in this distance. The angle it makes from one side of the sun, so 6 months later compared to the other side of the sun, that gives you what's called the parallax angle, which would be the right angle triangle here. And if you can measure this angle, it allows you to use trigonometry to determine the distance, because we know the distance to the sun. Okay, so this is basically the method used. Which statement is correct? Measurements are made against more distant stars. So you're basically seeing this star against more distant stars, like constellations for example, shifting from when you are on one side of the sun to the other in small amounts, and by that shift against the more distant stars you're able to work out the angle that is shifted at, and from that use trigonometry. Okay, so here it says B, just it's worth going through. Stellar parallax can only be used for distant stars. No, I told you it's really for nearby stars, and that's relative because everything is far away in space. So distant stars, that's why it's wrong. Okay, luminosity of the star must be constant. No, there's no reason for it to be constant. You're just looking at the angle. So as long as you're looking at the same star, we're looking at the angle, not to do with luminosity. It's irrelevant. The parallax effect is greatest for the most distant stars. Well, no, because if they're very distant, you won't see an angle change. Okay, so these angles can now be measured to quite a small degree, but obviously the further away the star is, the smaller the angle will be. So as you go further away towards this side, yeah, the angle will get smaller and smaller, and that it limits your ability to go to more distance. So this is a good revision of what stellar parallax methods for measuring distances in this topic. The next question is question 3. Yeah, just going to adjust the position at the top of the page so I don't need to do it each time. So we'll start at the top of the page. Okay, so the mass of a muon. Okay, so it's particle physics. You would have met this in Unit 4 as well. is 0.113 mass units. Remember, 1 mass unit can be converted into kilograms, and that's on your data sheet. Okay, so it's 10 to the minus 27 kilograms. Okay, you need to look at it because you can see here you have two of them very, very close together. So it's 1.66, not 1.67, which is a bit of a mean differentiation. The answer is actually C, but let's look at why. Which of the following is equal to the equivalent mass energy in joules? So you've got to change it into joules. Well, if you got the units, first you've got to change it into kilograms. So you've got to use the 0.113 units, convert it by this. This is how much each unit weighs, or has the equivalent of mass in kilograms. So you multiply the 0.113 units by the mass of each unit, and then to get the energy in joules, you use E equals mc squared, where this is kilograms and c squared is the speed of light. Okay, so the answer, if you look at the data sheet, will be C, and you can see these are very, very close. So it's a little bit of a mean question. A mass, question 4, a mass is oscillating with simple harmonic motion. So simple harmonic motion is anything where the acceleration is in a negative direction compared to the displacement. Okay, this is a defining equation for simple harmonic motion. Which statement about the acceleration of the mass is correct? So we have to look. So D is the answer. So you can see the acceleration is always towards the equilibrium position, because if you pull, for example, a pendulum is the easiest thing. If you pull a pendulum to the right, it will accelerate to the left. Yeah, you pull a pendulum to the left and it will accelerate to the right. So it's always in the opposite, and it's always towards the center of the equilibrium position, to the center where the equilibrium position is. So you can work this out as D. Okay, so it must be towards the equilibrium position because it's trying to rebalance itself. Question 5. Which of the following correctly describes the spontaneous nature of radioactivity? Well, that's, we cannot influence it. We don't know when the decay will occur. That spontaneous means it's not up to us. You can't influence it, and it's not known why a certain radioactive isotope will just spontaneously decay. Okay, this one we cannot predict is different, so we cannot influence its spontaneous nature. We cannot predict because it's random. Okay, so random and spontaneous are slightly different, and it's easy to get confused between the two. Okay, so I'll let you struggle with why the other ones aren't correct. Okay, and then you should go back and revise if you're still confused. Question 6. The planet Mercury orbits the Sun in an elliptical orbit. As a result, the speed of Mercury varies as it orbits the Sun. Okay, which is what elliptical orbits imply. When they're closer, they'll speed up. When they're further away, they'll slow down because the gravitational forces are inversely proportional to the separation. Which row of the table shows how the speed here and the gravitational potential energy change as Mercury approaches the Sun? Well, as Mercury approaches the Sun, it's getting closer, so you could almost think of it as mg delta H. Yeah, the mass of the Mercury times the gravity of the Sun. The distance is decreasing, so it will decrease. Okay, gravitational potential energy. So if you simply wanted to use that method, you could. So you know it's going to be decreased as a concept, and the speed will increase as it gets closer. So we've got increase in speed because as it gets closer, the gravity is stronger, and therefore it will speed up. Okay, the potential energy decreases, but the speed increases. So the answer is B. Question 7. Another simple harmonic motion question. A mass oscillates with simple harmonic motion. The mass has an angular velocity of 2 radians per second, so omega is 2 radians per second, and a maximum velocity of 10 centimeters per second. And we know from the equation at the back that the maximum velocity is when the displacement is at the amplitude, A omega. It comes from this equation, and obviously V max is when sine omega t is a maximum. When sine omega t equals 1, then the maximum velocity will be achieved. V equals A omega. Okay, the direction is just to show you that it's come from the displacement would have been positive, so the velocity is negative. Okay, so it would come from a differentiation, but you don't need to worry about that right now, I don't think. Which of the following gives the magnitude of amplitude A, so we want A of the oscillation in centimeters. Well, since V max equals A omega, then we can change the subject of the formula to put it as V max over omega. We know V max is given to us as 10 divided by 2 for the omega, and you get 5. So it's 10 over 2, but they want it in the form that we put it, which is B. Okay. Question 8, as we come towards the latter half, the latter end of the multiple choice. Mixture of helium and hydrogen gas is kept at room temperature, so they've got the same temperature. Which of the following is correct? The mean kinetic energy of helium is greater, means than the hydrogen. Well, no, because the mean kinetic energy is proportional to temperature, and they're both at the same temperature. Okay, so these two are wrong. One says greater, one says less. No, they should be the same. Mean kinetic energy is proportional to temperature. Okay, I think there's a half mc squared equation at the back. You need to go and look at it, and this will be proportional to temperature. So go and find that equation if you don't remember it. Okay, so these multiple choice questions are a really good way of last minute revision. So we're looking for D as the answer. So the mean square velocity of the helium molecules is less than the mean square velocity of the hydrogen molecules. Why is that? Okay, so because the mass of the helium molecules is greater, the mean kinetic energy should be the same. So if the mass is greater, the velocity should be less, not greater than. So these are two opposite questions. So the mean square velocity is how we work out the value in the kinetic theory of gases. Okay, so the answer is D. Okay, we're on to the last page of the multiple choice, question 9. This graph shows the radiation intensity, how the radiation intensity varies with the wavelength for star X and star Y. Okay, so basically from the peak wavelength, you can determine something using Wien's law. Okay, so we know Wien's law is lambda max is proportional, inverse proportional to temperature. Okay, now if you look at the equation sheet, you'll see the exact form. When you multiply temperature by the lambda max, you'll get a constant, okay, for each time. So the surface temperature of star X is Tx, okay? So this one has a Tx temperature, and therefore this one will have a Ty temperature, okay? Which statement is correct? Okay, so we're looking for D as the answer. Tx will be greater than Ty, okay? So Tx will be greater than Ty because the maximum wavelength is shorter. Well, just from common sense, you know if the maximum wavelength is shorter, it means the frequency is higher, the average frequency, if you like. So that's the peak frequency will be higher for the one with a lower wavelength, and frequency and energy are related, so therefore it must be due to the temperature. Okay, because peak intensity of star X is at a higher frequency, so that's the answer. C is the opposite, so it's incorrect. F peak will be proportional to temperature because wavelength peak is inverse proportional to temperature. Okay, so you can then have a look at A and B yourself. I don't want to spend too long on all the multiple choice questions because these videos can get quite long. Okay. Question 10. The Earth has 10 times the mass of the Mars. So I've just put it as an algebraic expression, and twice the radius of Mars. So we know these two equations. We also know that G equals gm over r squared. So the gravitational field or strength of the surface at the surface of the Earth is G Earth. So that would be equal to gm over r squared. But I've changed it, putting the Mars values in there because they want us to work out the relationship, which of the following gives a relationship between GE and GM. Okay, so this is GE, this is GM, so I've put the Mars values in both equations. So for Earth, I've put 10 mass of the Mars. Now that will allow you to divide 1 by 1, and which gives a relationship between GM and that, and you can then cancel out all the values, and you'll see that you're left with a ratio of 10 over 4, which is 2.5 times. Okay, so the gravity of the Earth is 2.5 times the gravity of Mars, and that ends the multiple choice section. So we're going to keep going with the shorter questions. Usually I do up to question 15 in the first video, if you've seen my previous videos, and then do the longer questions in a separate video. Okay, so question 11 is the first question in section B, and this is a Hertzsprung-Russell diagram, which shows some groups of stars. So these ones in the middle are called main sequence stars. They want you to know that you are familiar with the Hertzsprung-Russell diagram. So these are main sequence, these are giant stars, and these are white dwarfs. So P, Q, R, and S refer to different areas of the diagram. Describe a possible evolutionary path for stars originally in P. So P is a larger star. So as you go here, the stars are larger. As the Sun will be around here. Okay? So the Sun is a smaller main sequence star. P is larger, so we'll be closer to R. But regardless, all these main sequence stars basically go from P to S when they run out of hydrogen, and then they burn helium or larger nuclei depending on the size of stars, and when they run out of fuel they basically explode and die, and the center of the star becomes what's called a white dwarf. Eventually it's white because it's still glowing from the heat, and eventually it radiates all its heat energy and it becomes darker and darker, and it's basically a dead star. So for each phase, so we're looking at the evolution is from P to S back to Q. So they're looking for you to be able to describe it. Yeah. For each stage in the path, you should refer to the type of star. So they want you to know main sequence stars, and then they want you to say that it evolved into stars in area S, which are red giant stars, or they could be, if they're larger, supergiant stars, red supergiant stars. Okay, the higher up they are on the main sequence towards the top of this main sequence line, the more likely they are to be red supergiant stars when they go into the next phase of their evolution. And when they run out of fuel to carry on the fusion process, stars S will evolve or die into white dwarf stars, which are in area Q. And that's how you get the 3 marks. Okay, so that's the end of the first section B question. The next one is about a simple pendulum. Okay, so one of my students, he got completely confused and he didn't use this equation. So the pendulum equation, I always use the pendulum for many different levels of experimenting. T is equal to 2 pi square root of the length of the pendulum divided by G. This is in the equation sheet. They've given us the period as 2.00 seconds, so they're giving us values to 3 significant figures. Yeah, that gives you a clue as to how many you need to put your answer to. Calculate what the period would be if the pendulum was on the planet Venus. So basically, if you know what it is on Earth, the only thing that changes is gravity, but they want you to work it out based on the mass. Okay, so the mass is given, so you can work out G for it. Okay, so for Venus, given the mass and the radius, you can work out the gravity on Venus is 8.87 newtons per kilogram compared to 9.81 on Earth. So basically the ratio of the tension of the period is proportional to the square root of gravity. So you could say the period, did I say tension? Period of Venus over period on Earth is inverse proportional to the gravity. So therefore the gravity should be opposite way around in the fraction and a square root sign above it. So you put the values in and you'll see that it should be 1.05 times the period if you do the experiment on Venus. I wouldn't recommend it. It's not a very nice atmosphere. Okay, so once you do that, you will get 2.10 seconds. Question 12. Question 13. A particular line in the spectrum of light from a source in the laboratory has a frequency, normally I've called it F0 just to say that it's not moving, of this many hertz. Okay, 6.173 times 10 to the 14 hertz. The same line in the spectrum of light from a distant galaxy, so we know it's the same line in the spectrum due to the same transition, has a frequency which is lower. Okay, so there's a change in frequency. Decrease in frequency means an increase in wavelength, i.e. it's a redshift. That means we know it's moving away already. Okay, so this is what they're going to ask us. So we already worked it out. So whenever I'm reading the question, I'm underlining it and I'm absorbing the information, and I'm kind of already know what they're going to ask me. Deduce what can be concluded about distant galaxy. So I've already worked it out. you should include a calculation. So this, we know it's moving away, but they want you to know how fast it's moving away. So first of all, I actually was a bit, what's the opposite of dyslexic for numbers? I got the numbers wrong way around. I think I put 624, and therefore I got the number difference wrong. So difference in frequency is a difference in that. So it's a negative change. The frequency has gone down. Okay, so that's how we know that the wavelength has gone up. Yeah, therefore it's moving away from us, and therefore you can put the values in. Yeah, the shift is negative. Yeah, the final minus the initial. Okay, that's how you do the difference. That's why it comes out negative, because you put the final, if you like, this one, to compare to the normal one. Yeah, it's a negative change. So once you know that, you know V over C is also, so these are called Z values. Yeah, in the equation in the back. So both of these are equal to Z, the shift in the frequency compared to the normal frequency, and the velocity compared to the speed of light, gives you a ratio that you can then, we know C, we know the change in frequency, and we know that. You just change the subject to formula around, and you work out the recession velocity. Yeah, means it's moving away, is minus 1.51 times 10 to the 6. Remember, I've done it to 3 significant figures here. They've given us 4 significant figures there, but I think 3 significant figures is sufficient. So distant galaxy has an increase. So distant galaxy has a decrease in frequency, which is an increase. A decrease in frequency, which should be an increase in wavelength. Look, even there I would have lost a mark, even though I've got it right here. An increase in wavelength, which means it's redshifted, which gives a negative velocity, which means the galaxy is receding or moving away from the Earth. Okay, so those are the 3 ways, the 3 points that you get the marks for. Okay. That's question 13. Question 14 is about gas laws. So we're going to go to this equation, PV equals NKT. This is in your equation sheet. A tire on a racing bicycle contains nitrogen at a temperature of 22 degrees centigrade. Remember, you've got to change it to Kelvin. Just changing it to Kelvin gets you 1 mark, I think. All right, the nitrogen in the tire has a volume of 2.85 times 10 to the minus 4 meters cubed. The pressure of the nitrogen in the tire is so much. So this is the initial. So this is all initial values. And then nitrogen is pumped into the tire, so it means more nitrogen is pumped into the tire. The volume remains constant, so the volume doesn't change. The total mass of nitrogen in a tire, including the added nitrogen, is 2 grams. So we know the total mass of nitrogen, okay, is 2 grams. And we know know the molecular mass of nitrogen as well. They're giving it to us, okay. So we know that the mass in grams, or whatever, in the SI units will be the number of atoms times that, okay. But remember, this is equal to 2.00 times 10 to the minus 3 kilograms in SI units. Okay, so they're giving us information, they're giving us this, they want us to work out how many molecules there are, which is N. So you divide the mass in kilograms by the mass of each nitrogen molecule. That tells you how many nitrogen molecules there are in the final situation. So the final values. Okay, so this is a final value rather than initial. So we know the PV equals NKT. So we want to work out the final pressure because we already know the initial pressure. So the initial pressure is that. We want to work out the final pressure. Okay, so once we know the final pressure, we know the volume hasn't changed. So I've put P as my brain's not working today, so I'm just suffering from a little bit of cold. So P equals NKT over V. N we know from here. K is from the data sheet. T is the temperature in Kelvin, and the volume didn't change. So there's the volume, which is the initial volume as well. Gives you a final pressure, yeah, or the new pressure of this. We know the initial pressure, take the difference, and you work out the change in pressure is that much. And I've missed the units, so I could lose some marks. Okay, 3.6 times 10 to the 4. So be careful if you, and you meant to write it all in there. If you miss the units, you will lose a mark. Okay, easy to do, as you just noticed. Okay, that's question 14. Question 15. A teacher used liquid nitrogen. So we went from nitrogen to liquid nitrogen to demonstrate low temperature physics. The teacher dropped a peeled banana at room temperature into a flask of liquid nitrogen. Explain why the liquid nitrogen boiled, okay, when the banana was submerged in the liquid nitrogen. Well, thermal energy is transferred from the banana. This is what they want you to tell. So heat always moves from high temperature to low temperature, okay? So the thermal energy is transferred from the banana at room temperature to the colder liquid nitrogen, okay? So you need to talk about energy transfer. Second point, this energy is sufficient, or must be sufficient, yeah, to raise the temperature of nitrogen to its boiling points using the specific capacity equation. You will probably have to do that later on. It looks like they're giving us data later on to do something like that. And must provide sufficient energy to allow a change of state, yeah, because it says it boiled. So it boiled means it's changing state, so it raises it first, and then it also has enough energy to provide the latent heat of vaporization required to break the bonds. Okay, so that's the first part. I hope that makes sense. Part B, during the demonstration, the liquid nitrogen remained at its boiling point in a large flask, so it didn't go beyond the boiling point. That means after it was changing state, it didn't have energy to then go into a higher temperature once it's reached a gaseous state. So it stays in the transition. So all the energy goes to breaking the bonds. The teacher estimated that at least 0.5 kilograms was needed of liquid nitrogen to cool the banana from room temperature to temperature of the liquid nitrogen. So now talking about cooling. So in other words, so they're telling us this is the estimate, yeah, that the mass of nitrogen would be 0.5 kilograms. So we got to work out whether the teacher's estimate is correct. So it says assessed the accuracy of the teacher's estimate given this data. So they're giving us the latent heat of vaporization of nitrogen. They're giving us the boiling point of nitrogen, 77.4. And we know the room temperature, presumably. Yes, there it is. So we know the change in temperature. We know the mass of the banana. And we know the specific heat capacity of the banana. Okay, so we've got MC delta T. Okay, so calculate the mass of nitrogen needed. So we're going to calculate the mass of nitrogen needed and then compare it to what the teacher's estimate was and see if the teacher was accurate. For the banana to cool from room temperature 292 to boiling point of nitrogen, the temperature change must be 292 minus 77.4. So you have to work out the temperature change. You put in the mass of the banana, the specific capacity of the banana, and you come up with the energy to cool the banana, yeah, from room temperature. So that's the energy required to cool the banana. Once that happens, this energy must be provided by the liquid nitrogen, changing state. So it's cooling the banana, and therefore the energy from the nitrogen, yeah, must be from the changing state. So it must be the E equals ml equation. So this is the energy, this is the mass of the nitrogen, and the mass of the nitrogen is it given to us? No, we're working it out. So they've given us the latent heat of vaporization of the nitrogen, yeah, as 1.98 times 10 to the 5. So we want to work out the mass of nitrogen, and we just worked it out there. So the energy, if it's sufficient to cool the banana by that much, so we're using the energy needed divided by the latent heat of vaporization that they've provided us with, and we work out the mass of nitrogen required is only 0.225. This shows the teacher overestimated. Yeah, sorry, I missed it. I do this quite often. I was zooming into the thing, it makes it very clear on the video. Sometimes I forget to move it up. So the energy provided. So basically this is the energy we need to cool down the banana. And this is provided by the liquid nitrogen, changing states. So therefore, changing state is this equation. We want to work out, in theory, how much mass of nitrogen you would need. So we're using the energy to cool the banana divided by the latent heat of vaporization of the nitrogen, and we come up with only 0.225, which is less than the 0.5 kilograms that was estimated that the teacher said. So this shows that the teacher overestimated the mass of liquid nitrogen required by 0.27 kilograms, so the teacher's estimate was not accurate. So you must drive the point home to get the 3 marks. Okay, quite a lot to do for 3 marks. Okay, that's question 15, and I think, let's just have a look. So we've done question 15, we got question 16, 17, 18, coming up 19, and That's a long question, 19. And then we got question 21. So let's try and do another question. Okay, so Pluto is a dwarf planet in the outer regions of the solar system. Pluto moves in an approximately circular orbit around the Sun. The mean radius of the orbit is given as this distance. And to calculate the intensity of radiation from the Sun incident on Pluto, there is an equation on your equation sheet where it shows the intensity of a luminous object at a certain distance is the inverse square law. So this is the d you put in there, and you can work it out where the radius of the Sun is given, yeah, and the surface temperature of the Sun is given. Well, to be able to work out the luminosity of a star, you use Stefan Boltzmann's equation, which is this, which is also on the formula sheet, where this is a constant. A is the area of the Sun, so you've got to use this value to work out the surface area of the Sun, because obviously that's where the luminosity comes from, and the temperature is to the power of 4. So this is the equation where you can work it out. First, you've got to work out the area is 4 pi r squared. So remember, it's a sphere. The surface area of the sphere is 4 pi times the value given here for the Sun. So that gives us a surface area of the Sun of 6.09 times 10 to the 18 meters squared, rather large. And there for the luminosity Sun, this is the constant which I said is sigma. A is what we just calculated, and 5,800 is the temperature to the power of 4. I've had students where they forget to put the power of 4, get the wrong answer, lose marks in a very simple way. So once you've got the luminosity, that'll give you another mark. Then once you know the luminosity, remember you're using this equation, the luminosity of the Sun at the distance of Pluto will decrease, the intensity of the light will decrease using the inverse square law at Pluto's distance. So you put the luminosity we calculated here into the equation, divided by 4 pi, this times the distance to Pluto, yeah, 10 to the 12, 5.91 times 10 to the 12, you've got to square it, don't forget, you get the intensity of 0.89 watts per meter. So I think 2 significant figures is sufficient, but I always tell my students when you're calculating it, show your final answer 0.3, and then you can say you've rounded up to 2 significant figures. Okay, I'm sure these values are not that accurately known. Remember, so the temperature of the Sun is known to 2 significant figures, so it's 2 or 3 would be acceptable, and this allows you to hedge your bets and have 2 and 3 in your answer. Okay, calculate the time it takes in years for Pluto to complete one orbit of the Sun. Okay, so we're on a period of orbit, so it's circular motion, so you need to be aware that circular motion is gmm over r squared, the gravitational force, is equal to mr squared, mr omega squared. M's cancel out, so you don't really need to know the mass, but you do need to know the mass of the Sun, so that's this big M, okay? And so this allows you to work out the angular velocity, because we know g, we know m, and we know r, okay? So that's the same distance. So we're talking about the angular velocity of Pluto. So you've been using the distance of Pluto this time. You've got to cube it. Yeah, so if you simplify the equation, you'll see this is an equation that will always be true. Once you do that, you can work out the angular velocity in radians per second, and then you need to realize that t, the period, is 2 pi over omega. So this is equations that you studied before. You do the maths and you get to this many seconds, and they've given us 1 year, and they want you to work out it in years, 249 years, which is approximately 3 significant figures, or approximately 250 years if you don't want to be that accurate. Okay, so how many figures should you use? Probably 3. They got 3 data there. Most of them are 3, so 249 years would be okay. But this does no harm doing it both 3 significant figures and 2 significant figures. Okay, so that's question 16 done. That's where we're going to stop because I need a break, and then we're going to come back and look at question 17. I'll leave it on the screen so you can have a look at it if you want to freeze the video. So thank you very much for watching, and make sure you subscribe when you can, so you will know when the second part is ready, plus any future videos. And also, as I requested before, we've got 160 subscribers now. We want to increase our reach so more students can benefit from improving your exam techniques. So please like the video so it gets us higher in the rankings in YouTube, however it works, the algorithms, and share it with your friends if you know people doing the same exam. Okay, and please feel free to comment in the comments. Okay, that's it from me for now. Bye for now. See you in the next video. Bye.